Welcome to DP Tutorials by Donny Jerwa. In this teaching module, we will learn on another topic, which is the electric field due to a uniformly charged spherical shell. Now, while studying this important case, we have to remember that it is the application of Gauss Law of Electrostatics. It is the application of Gauss Law of Electrostatics. In Gauss Law of Electrostatics, we have learned that the electric flux, we have learned that electric flux phi, it is equal to the line integral of E dot ds. And this electric flux, it is equal to 1 by epsilon naught times the charge enclosed by it. So in this case, we have considered this spherical shell having a certain radius r, and along the outer surface of the spherical shell, we have these positive charges which are residing on its surface. So over here, we have this charge q, and all these charge q are uniformly distributed along the outer surface of the shell. And since the charges are considered to be positive, we know that the electric lines of force will be pointing radially outwards. And these electric field vectors will be, the electric field will be represented by a vector which is E. So in this case, if this will be 1, this will be the direction of our electric field line directed in that direction. Even in this case also, this will be the direction of our electric field line directed in the outwards direction. So from here, it is very clear that if I want to find the electric field due to this spherical shell, we have to consider for certain cases. Number 1, for a point which is outside the shell. Now when I say for a point which is outside the shell, that means it is supposed to be beyond those positive charges, beyond those positive charges, and there will be another point which is inside the surface. So like for instance, if I consider this point over here, that point, if I consider that point P over there, that means this will be one point which is outside the surface. This point, this is outside the surface. If I consider another point over here, that point Q, this is point Q which is on the surface. Okay? This Q which is on the surface. And if I consider another point, suppose X, this point X is inside the spherical shell. So you have to study the electric field. You have to study the electric field for different cases. For a point which is outside the spherical shell, for the point which is on the surface of the spherical shell, and another which is inside the spherical shell. So for different cases, we will study them independently. Okay? So now we have already learned that if I want to find the electric field, like for instance at this point P, which is outside the spherical shell, we have to consider a Gaussian surface. We have to consider a Gaussian surface. That means this surface will enclose all these charges inside. That is why we have to construct these Gaussian surface, and the surface which we have considered that we will choose over here will be what? Will be a spherical surface which will enclose all the charges inside. And this spherical surface will be having a certain radius r. So from here, we will choose this spherical surface. We will choose this spherical surface, and we will make sure that this spherical surface will enclose that point P, which is outside the spherical shell. So I'll take this spherical shell, which is at the same center, and then let that point P, this point P be somewhere at a certain distance r. Let that point P be at a certain distance, okay, let this point be that at a certain distance, suppose small r, from the center O of the spherical shell, then likewise over here also we have to know that the electric field intensity at point P is given by what? Is given by the electric field vector. So in this case, we will take the electric field vector and let this blue ray represent our electric field vector towards, okay, or coming from point P. So this will represent our electric field vector. So let this be our electric field vector denoted by E bar, okay, denoted by E bar. And then now we know that all the electric lines of force will be directed what? All these electric lines of force will be directed in the outward directions, okay, in the outward direction. Now this electric field line, we make sure that it should be coming only from the surface of the shell, because there are no electric field lines inside the shell. So the electric field line should always be coming from a surface which is inside the shell. So that is why when you represent them, you have to represent them very, very carefully, like that, okay, like in that way. So it should come outside of the shell. So all these will be all these will be our electric field lines, whatever the point may be. It might be from this point also. This will be this will be the direction of our electric field vector. Then suppose if I consider a small element over here, let that elementary surface be ds, then with respect to that point, we have to draw what? We have to draw a area element. Say like for instance, if I consider over here, that means if this is our ds area element, then the area element vector perpendicular to ds will be this vector acting on this direction. So this will be what? This will be our ds bar. So in the same case also, we will take another vector, this yellow dotted vector, and this ds bar and this ds bar, and this vector will be pointing in the same direction. So it is very, very evident from here that this ds bar acts in the same direction in which the electric field vector is acting. Even if I consider this area element over here, that means if I draw the area element vector, that means both E and ds are acting in the same direction. So now we will study what is the flux through that area element. Okay, we will study what is the flux through that area element. So in this case, from Gauss law, it follows that the electric flux through this point P, is given by the expression, okay, it's given by the expression phi equal close integration of E dot ds, I have to put this vector notation, and this will be equal to 1, Q divided by epsilon naught, okay, where epsilon naught is our absolute permittivity of free space. And from here also, it is very, very evident that this E and ds are what? Are acting on the same direction. If E and ds are acting in the same direction, then the angle between them is 0 degree. Okay? The angle between them is 0 degree. So it follows that the electric flux, okay? Therefore the electric flux denoted by phi, which is the surface integral or the line integral of E and ds will be equal to close integration of E ds cos of 0 degree. But cos of 0 degree is equal to 1. So in magnitude, we have only E ds into 1, which is equal to the surface integral of E and ds. But this electric field, okay, this electric field, it is constant to all the entire surface. This electric field E is constant to all this spherical surface or that Gaussian surface. So if under the condition that if E is constant, if E is constant, then we can take that E outside, and then we are left with closed integration of ds. Okay? Closed integration of ds. But also when you look closely, that we have to solve. What is this closed integration of ds? This closed integration of ds, that means it will be the surface area of that Gaussian surface. Okay? The surface area of that Gaussian surface. Say if you look on this Gaussian surface, if I consider all these small elements, okay, I draw all these small elements, and if I sum over all these small elements, that means it will be equal to the surface area. Okay, it will be equal to the surface area of the that Gaussian spherical shell, which is of the shape of a sphere. So from here, that means this will be equal to, okay, this will be equal to 4 pi. So it should be 1. It should be small r square. Why small r square? Because the radius, okay, the radius of the outer spherical shell or of the spherical shell is small r square. So we will substitute on that condition. Say we will mark this as equation number 2. So when I put that as equation number 2, it follows from here that this electric flux phi will be equal to E into 4 pi r square. Okay, 4 pi r square. So from here, if you substitute further for finding the on equation 1, it follows from equation 1. It follows from equation 1. Okay, it follows from equation 1 that this phi is q divided by epsilon naught. So over here, phi will be equal to q divided by epsilon naught. This will be equal to E into 4 pi r square. Then if I solve on the other part, that means in order to find E, that means over here, after solving, we will find out that this E will be equal to 1 by 4 pi epsilon naught q divided by r square. This is the expression, okay? This is that expression for the electric field. This is that expression for the electric field at a point which is outside the spherical shell. That means this is the working formula. So this electric field at a point which is outside the spherical shell is given by this equation, which is equal to this expression. And we have to be very careful that this expression is similar to the expression for the electric field due to a point charge. It is similar, okay, to the electric field due to a point charge. What does it physically means? It physically means that if I consider all these charges, that means for a point P, that means for this point Q, or for any point which is outside this spherical shell, that means all these charges will assume to be as if they are concentrated where? At the center of the spherical shell. So that is the main importance. It does not depend, okay? It does not depend upon the thickness, but it really depends upon the radius r. So when you look closely from this equation, that means it depends, okay? That means this E, this electric field, it is dependent upon the distance. As you take the point P farther, very far away from O, so E will be less. So which means like this: if R is large, then E will be less. And when E is small, when this R is small, okay, when R is large, E is less, and when R is small, that means E will be 1, E will be large. So these are the physical interpretation of different cases. Then next we will consider, suppose now we will consider let that point P, okay, let us take a point which is where, which is on the surface. So this is the point which is outside. If I take another point here, if I assume another point here, that means this will be the point which is on the surface. And if I assume another point over here, that means this will be the point which is what, which is inside the shell. So this will be the first case number 1, then this will be case number 2, and this will be case number 3. For the point which is outside, that means this E is inversely proportional to 1 divided by R square, or we can write Q divided by R square. Then we will find out for this point. Okay, for the point which is on the surface, that means you have to assume a point over here. You have to assume a point over here which is on the surface. Okay. Now, when you look at this, this is our charged spherical shell having a radius r. Then if I take any point, okay, any point, say like Q, this point is Q which is on the surface, or if I take this point also X which is on the surface, that means if I want to find the electric field even from here also will be in this direction. So this will be the direction of our electric field lines. Even at this point also, this will be the direction of our electric field line. Then if I want to find out the electric field at the point Q which is on the surface of the shell, then I have to do what? I have to consider a Gaussian surface or construct a Gaussian surface across that point. Then I will take this Gaussian surface and I will take this Gaussian surface to be in such a way that this red shaded spherical surface encloses all those charges inside it, okay, which it means that for a point which is on the surface of the shell, okay, for a point which is on the surface of the shell, what does it mean? It means that, see from here, capital R will be the radius of the sphere. And what about this radius of the spherical shell? The radius of the spherical, of that red colored dash Gaussian surface will be what? Will be small r. In that case, for a point which is on the surface of the shell, it means that the radius of the Gaussian surface is equal to the radius of the spherical shell. In such cases, it means that the electric field we have solved previously, the electric field will be given by this expression, 1 by 4 pi epsilon naught, then Q divided by R square, small r square, okay, Q divided by small r square. Then we have to use this condition for the point which is on the surface. Then in place of R square, we have to write what? We have to write capital R square, okay, capital R square. So this is capital R square, which is we can write further in a simplified manner, which is 1 by 4 pi epsilon naught divided by R square. This is the case for which the electric field will be 1. The electric field will be maximum. The electric field will be maximum. Then we will choose the point which is inside the surface, okay, for a point inside the shell, okay, inside the shell. So for the point which is inside the shell, yes, for the point which is inside the shell, so if I take any point, suppose I take this point which is inside the spherical shell, and for any point considered, you have to always construct a surface across it. See, if I take this point Q, that means I have to construct a surface across that point Q. So that is the physical significance, okay, that is the physical significance of taking that arbitrary point. It might be inside, it might be on the surface, or it might be outside the surface. Then suppose I will take any point P, any point which is on the surface. Say like for instance over here, this is our spherical surface, Gaussian spherical surface. Let us consider this point P. Okay? Let us consider that point P again. So from here we have taken this point P which is on the surface, and we have constructed a Gaussian surface. When you look closely from here, we find out that all these charges, okay, all these charges are on the surface. The charges are on the surface. The charges are on the surface. While for this point Q, there will be one. For this point P, I mean, there are no charges inside. Okay? There are no charges inside. So for a point which is inside the shell, yes, for a point which is inside the shell, there will be no charges inside. Okay? So for a point which is inside the shell, there are no charges. Under the condition that we have assumed that all these charges are residing on the outer surface. So no charges are located inside. No charges are located inside the shell. So if no charges are located inside the shell, what does it mean? Physically, it means that the charges will be equal to 0. If charges are equal to 0, if you put on that equation, if there is no charge, there will be no electric field. So here Q, that Q will be equal to 0. Then you have to put over here 4 pi epsilon naught, okay, 4 pi epsilon naught into R square. What is R square? This is your R, and from here this is our capital R. Then when you solve, you will find out that E will be equal to 0, which implies that the electric field inside the spherical shell will be equal to 0. So now you have to also study some idea related to graph of the electric field versus the distance. So when you look at the graph of an equation, we find out that number one, okay, for a point which is outside the spherical surface, okay, for a point which is outside the spherical shell, the formula will be E equal 1 by 4 pi epsilon naught Q divided by R square. And then number 2, for the point which is on the surface, okay, for a point which is on the surface, E will be equal to Q divided by 4 pi epsilon naught capital R square. And for the point which is inside the spherical shell, our electric field is 0. So when I draw any sphere, and if this is the center O, that means all the charges are residing on the surface of the spherical shell. Okay? All the charges are residing on the surface of the spherical shell, which means that the electric field inside will be 0. That means as you move from the center, as you keep on progressing till you reach the surface, that means at the surface of the spherical shell, the electric field will be 1. The electric field will be maximum. As you consider for the point, say like for instance, if I take this point P with respect from the center, or if I take another point, okay, if I take another point Q which is away from the center, say this point is how much? This point is Q. So that distance from O, this distance from O up to this point, this is the radius of the spherical shell. If I take this another radius, suppose R1 of point P, and from O up to Q, that will be R2, which from the figure itself, it means that the radius of point Q, R2, is more than the radius of point P, which is R1. So in this case, as the distance increases, what does what can you relate from the electric field? The electric field at point E1, okay, the electric field due to point Q, the electric field due to point Q will be will be less than the electric field due to point P, or electric field at P is more than electric field at Q. So that is why from here, when you plot this graph of the electric field and the distance, okay, as you move from the center to the surface, the electric field will be 0. That is why it is represented by this curve. Okay, from O, this is the radius. This is the capital R. Capital R will be 1, the radius of the sphere. From 0 till it reaches, that means from here again, from 0 till it reaches 1, till it reaches the surface, the electric field will be 0. The moment it reaches the surface, then what will happen? The electric field will be maximum. Okay, that is the point. The electric field will be maximum. This is the point which is where? Which is on the surface. Okay, so this at the center. This is the point which is electric field at the center. When R is equal to 0, E also is equal to 0. Then for the point outside. For the point outside, that means as distance increases, as we increase this distance onwards towards this point, what will happen? The electric field will decrease, because for the point which is outside the surface, E is inversely proportional to 1. E is inversely proportional to R square. So for graphs which are inversely proportional to R square, that means it is this type of graph. That means this is the graph. Suppose if I name this as O, and this is the point. Okay, wait. Suppose if I mark this point as point A, okay, this is the point A. At this particular point, the electric field will be maximum. This is the point corresponding to R is equal to capital R. From O up to A, that means this will be the point for the charges, which is 1, which is inside. This is the point in which the charges is where? It is located where? On the surface. Okay, on the surface. Suppose this is point, suppose B. OA, B. Point B is on the surface. Then this curve BC will represent the electric field, which is 1, which is outside the surface, and it is linearly decreasing. It is decreasing as the square of the distance, inverse of the square of the distance. So if you plot a graph paper for functions of inversely proportional to R, that means 1 by R square, all these functions will give you this type of graph. Okay, that type of graph. If you take for the function which is R square, okay, R square, that means you'll get a graph which is 1, which is a parabolic graph. Okay, a parabolic graph. So these are the types of graph which will express the variation of E versus 1 versus our distance. So just go through all these discussions for the point which is outside, the point on the surface, and the point inside the surface for more clarity. Thank you.